everyone. So today we'll begin our discussions on the topics of stress and strain. So we'll take up stress first, and for most of us, this is a relatively newer concept, especially when it applies to 2 and 3 dimensions. And this is what you can say is a big departure from your earlier course from APL 100. That's where we are sort of upgrading now to the next level. So let's take a brief overview. So in the second chapter, as the author in your textbook mentions, we have considered deformable bodies in which the loadings and resulting deformations were assumed to be unidirectional. So they were acting only in one direction. Like there was a bar which was extending or compressing along the axis. Okay. So then we had found out the relations between load and resulting deformation in terms of the shape of the body and the modulus of elasticity. So remember 2.1 equation in which there were three methods: force, equilibrium, deformations, and the third was the relationship between force and deformation. We did it under the assumption that the conditions were uniform from one point to another. Okay, meaning there was no jump or no change in the stress or strain for that matter across a beam. Okay, so that was the assumption, that the conditions were uniform from one point to another. Now we would want to extend our study for cases in which there is a non-uniformity of the deformations or forces, and we'll find it necessary to study the behavior in differentially small elements within the body. So now, I mean, you might not really have the whole body under the same conditions. Okay. Also, there is a need to go into 2 and 3 dimensions now, which we will for the remainder of this course as such, and that requires the development of certain theories which we begin doing it in this chapter. So the transverse deflection of a beam in bending turns out to depend on the distribution both along the and across the beam of the axial force per unit area. Okay, so this is something which we'll see, that we had only taken one V, okay, and the bending moment mb, but it turns out that the transverse deflection of this beam during bending will depend on both the uh, axial force per unit area along and across the beam as well. So we have to take it along two axes. Okay, now to derive all this, you need to consider very small elements of the solid body, like a differential element, and then apply the principles of equilibrium, geometric compatibility, and the relationship between force and deformation there, essentially equation 2.1. So now equation 2.1 will not be applied to a whole beam or a bar or the whole solid as such. It will be applied to differential parts of a three-dimensional solid. Okay, now we want to consider a localized behavior of a material at a point within deformable body. So this at a point is very important. So the stress which we would want to define, say if you have a three-dimensional body, we are trying to define what it is at this one point. Okay, and the same for strain at this the same point, and the same for relationship between force and deformation, or in this case between stress and strain at the same point. So that is one departure which we must clearly understand, that all this is done for a localized behavior in the body. Okay, So equilibrium at this point and the geometry of deformation at the same point are considered in remaining sections of this chapter, and in the future chapters we'll build upon this theory for various kinds of loadings in our problems. Okay, so let's start with section 4.2 in the textbook, which is stress. Now we must recall section 2.2, okay, in which we had found that the force and deformation in bars under tensile loading could be related to the material property, which was the modulus of elasticity. And then you could do that by considering force per unit area, and the extension was taken as per unit length. If you want, I mean, that was the Hooke's law. That's what we had seen in section 2.2. So let me just write down that equation. Okay. Section 2.2. Okay. So we had seen that in section 2.2. Please, I mean, you can go back and just see those examples and theory which we had read over there. Now you want to define the concept of internal force per unit area and how this can be extended to a more general shape and geometry, such has been shown in figure 4.1 over here. So let's consider this, the internal force per unit area. So this is what we would want to study first, okay, in a figure like this. So this is a continuum solid, continuous body acted on by external forces. You can see the external forces by the bold symbol F1, F2, F until Fn, and Fi is the generic force over here. All of them are external as it is defined. Now this solid has this point of interest O. Okay, O is an internal point in this solid. And what you do is we pass a plane whose normal vector is n. So this is the plane, okay, and the normal vector of this plane is n. So please look at figure 4.2. This is the normal vector of this plane, okay, and this is the same hypothetical cut which we have done, okay, for the beam bending and even the extension and compression of bars problems. So you have cut this continuum solid at point O using a plane whose orientation is normal vector is n. Okay, so let me just rub this out. Okay, now in order for the separate halves of the body to be in equilibrium, there must be an internal force transmitted across the cutting plane. Okay, so there are these internal force which you see by these arrows, and they must be acting so as to each half must be in equilibrium. Now remember this with respect to the beam which you had when you made sort of beam or a bar, when you made an hypothetical cut in it, the internal force which you were trying to find here, okay, was now becoming external, right? So the same has happened over here. These internal forces after this hypothetical cut, now they have become external, and hence we will apply ideas which were similar to that in the previous studies, in the previous chapters, and proceed. Only thing is, because of the complication in geometry, there are many new things which will come up, but the basic premise remains the same. Okay, so these internal forces transmitted across the cutting plane will be there, and they must be of a certain value so that equilibrium of each half is maintained. Now, if you divide the plane into number of small areas, how this is a number of small areas, these ticks, okay, they are all in small areas. Okay, you measure the force acting on each of these. So if this is the arrow which you are considering, this is the force acting on this area. Okay, similarly, this is the force acting on this area, okay, and so on. So this is what we mean, that if we divide the plane into number of small areas and we measure the forces acting on each of these, we will observe that these forces in general vary from one small area to the next one. The idea is that this force for this area will be different than, say, this force in this area, and so on. So in generally they will vary from one small area to the other. And remember, this is what we meant by saying non-uniform in the introduction which we were seeing. Okay, this was something which was not happening, say, when you took this beam earlier. You said that the shear force will be the same on this plane. Okay, it can vary with x, okay, but it was same at this place, it was same at this place, and it was same at this place. This was a uniform assumption, and now we are defining something which is non-uniform. Okay, okay, so now on the small area delta A, whose normal vector is n, centered on the point O. Now what you do is you take out this force, this normal vector, this A, and this area, and you see it over here. Okay, so this is what you have. You have taken out this one area which has a normal n. This force acting on this is delta F. With this is a vector, that's why it's in bold, and the area of this small part is delta A. Okay, whose normal vector is n, centered on the point O. So O is at the center. That is something which you should know. Okay, O is at center of this small area. They will be acting a force delta which is inclined to the surface delta A by some arbitrary angle. Now, when we consider the problem of describing completely the action of the force vector delta F, we have to specify the orientation and size of the face on which delta F acts, the magnitude of delta F, and the orientation of delta F with respect to the face. The idea is that you want to have lot of things known when you want to study this non-uniform internal force per unit area. And some of the things as they are mentioned is to specify the orientation and size of the face on which delta F acts, meaning you should be aware of n, then the angle which this delta F makes with the orientation, and so on. Okay, now we introduce a new concept. This new concept is called a stress vector. Okay, and this vector word is important, as you will see, and this is shown by this symbol T and N. Now in your textbook you have T and N as in this superscript in bold, not with an arrow, but as I have already discussed, I'll be showing you with an arrow because it's hard for me to boldify a symbol. Okay, so this stress vector acting at O on a plane whose normal is n passing through O. Okay. You want to define this. I mentioned this with the equality and there's a define symbols just to tell that this is a definition, and this is one habit which you can also take. Okay, sorry, it should be delta A, and then the limit on delta A must be that it tends to 0. So this is how we define a stress vector. Okay, and if you can see clearly that this is actually a force intensity or stress. Okay, acting on a plane at the point O. Now if you carefully read what I have written at least twice, I always mention about the stress vector acting at this point and on a plane. Okay, so both of those two things are necessary: the point at which this acts and the orientation n, which is of the plane which you have used for this definition. So that n appears over here, and this delta f must act at that point. Okay, and that small area is delta a. So this is the most important thing which you should know and learn at least by heart, that both the point of application of this force and this orientation of the plane n is required for defining a stress vector. Okay, so we have used this notation, and that also I have repeated again as well, the same part. So we have used this notation for the force intensity to emphasize that Tn is a vector and that it acts on a plane passing through the point O whose normal is n, like figure 0.43c, this figure. So this definition must be learned with this diagram. There cannot be a doubt about this ever. Okay. Now Tn in general does not act in the direction of n. So T of n in general is not parallel to n generally. Okay, as is also shown in this figure. So generally this is not the case. Okay, now in assuming the existence of this limit, so this is 4.1, equation 4.1. So you have, I mean, when you define it like this, you assume that this limit exists. Okay, limit exists. This is an assumption. Not all limits exist. You are already aware of this, right? There are many cases where the limits do not exist. Can you think of a couple of simple examples where limit does not exist? Okay, so take some time, and I think you should be recall of a couple of cases at least where the limit does not exist. Okay, so now in assuming the existence of this limit, we have in effect made a continuum hypothesis with respect to the distribution of internal forces. This is an idealization of the behavior in a real material where delta F decreases smoothly with delta A only when delta A is large in comparison to the microstructure of the material. So you can always question why, I mean, why this limit is existing. So this is how it works. In a real material, the delta F will continuously and smoothly decrease with delta A. Okay, and hence this limit can exist, but it must be, the delta A must be large with respect to a microstructure. So you may be learning a course in material science, so you can assume that that microstructure is the grain size. Okay, if you have not gone this far in your course until now, soon you will. So the idea is that delta A can be larger, or with respect to the grain size, and you will also learn in that course how to measure the grain size. So if you have this solid, so these will all be your grains. Okay, so this delta A, so this is one of your grains, and then you can have an average size of grain. The delta A must be larger than that. So that is the real case, and you assume this idealization. Okay, where the delta F and delta A can be treated. So there is a continuity in this, meaning this existence of this limit means, I mean, now you go to some other point which is near to O, a limit like this should exist there as well for that point, for that orientation, and so on. Okay, so this delta A must be there. Now this is where this idealization thing is coming up. The delta A in your definition is actually tending to 0, but the grain size will not be tending to 0, and hence actually this will not happen. Okay, so this happens in a real material, and this, what you are assuming that delta A should actually tend to 0, is your idealization of this situation. Okay, doesn't happen in reality, and this is also part of continuum hypothesis. What does continuum hypothesis do? It ignores these granular structure and crystals and so on in a material, or any other way you look at it. Okay, so this is what the continuum hypothesis does. It ignores these grains and grain boundaries in a solid and treats it like one continuous solid. So I hope this part is clear. If not, you can always discuss this with me. Okay, you will have to, because it's a new thing, so you'll have to focus and perhaps rewind and replay this video as it goes along. Okay. Now there are four major characteristics, as the author of your textbook says. There are four major characteristics of stress we must keep in mind. The first is that the physical dimensions of the stress are force per unit area. That's the easy part. The second is that the stress is defined at a point upon an imaginary plane, okay, or boundary dividing the material in two parts. Remember why this was an imaginary? Because this was a hypothetical cut. Okay. The third part is that the stress is a vector equivalent to the action of one part of the material upon another. So you know that just like for this beam, okay, when you cut it, you take this forces in this particular form. Okay, so similar, because of the equal and opposite nature at this intersection. So the same would happen over here as well. Okay, stress vector is equivalent to the action of one part of the material upon another. And the last part is that the direction of the stress vector is not restricted, in the sense it can have a unrestricted direction. I mean, there is no constraint on this direction. We have already seen, because it's generally, you see over here, it's generally not aligned with n, so it can be anywhere. Now this is what you do next. Since Tn, which is the stress vector, is a vector in 3 dimensions, you can write this vector, or for that matter any vector, in this form as I plus j cap plus k cap. Okay, so there is three parts to this, three components of any vector: one along the ith direction, j along the nth direction, plus k along the zth direction, in the z direction. So those components are written in this form. Okay, notice that these are actually scalars, tx, ty, tz. They are shown with this superscript n vector just to indicate that they still are linked to this plane at which they are defined. Okay, but they themselves are a scalar quantity, unlike the stress vector, which is a vector quantity. Okay, so there is nothing new about it. I mean, just the symbols are increasing in size, that's why perhaps it takes more time for us to grab them. Okay, now it is convenient in what follows to express the stress vector at a point acting on a plane whose normal is n in terms of the stress vectors acting on planes which pass through the point parallel to the coordinate planes. Mhm. So this is what we do. There is a convenience factor to what the author says. To define this vector Tn, okay, in terms Tn's acting on planes which pass through the point parallel to the coordinate planes, meaning acting on planes which are parallel to I cap, j cap, k cap. Okay, and that's what we want to do next. I'll explain this once more. Say you have this I, j and k axis. Okay, now what are the planes which are parallel to I axis? Say this plane. What is the plane which is parallel to j axis? Let's call this plane, right? And similarly you will have a plane which is parallel to the k axis, not drawing that. Now if there is any vector, okay, any vector, just happens to be the stress vector, but it can be any vector which is like this. Now this vector, as you know, is not parallel to any of these three planes, okay, any of these planes parallel to I axis, j axis or k axis. But you will find it convenient if somehow this particular vector can be written in terms of a vector which is acting on planes which pass through the point parallel to the coordinate axis. So if you can, let me use another ink. Sorry. Draw color. Okay. So this vector, the blue vector, would be nice to write this in terms of, say, this, this and this. Okay. Now the object, so that it can be written in terms of tractions acting on planes which are parallel to this. So this is on a plane which is parallel to the j axis, this is on a plane which is parallel to y-axis, and you can have a third axis as well. So you want to write this Tn in terms of these three green vectors because it will be convenient, okay? And that is what we will try to achieve now, okay? Because right now you can possibly have infinite orientations of this plane or orientations of this vector, I'm sorry, okay? Because it's an unrestricted vector. The direction of the stress vector is not restricted. But it would be nice to write it in terms of three well-defined vectors along these nice Cartesian planes. So that's what we want to do next. Okay, so let me switch back to the color. Okay. So once you have found these three components acting on the coordinate planes, we will relate these to the Tn. So once you find what these green ones are, you will relate it back to this vector, and then you will see the convenience of doing that over there. Okay, so let's see. Okay, so now let's come back to the discussion of the continuous body shown in figure 4.1. Okay, this was figure 4.1. Let me just rub off this. And now pass through the point O, a plane MM. Okay, so that's what you have done in this figure 4.4. You have passed through the point O a plane MM. So this is the plane MM parallel to the YZ plane. Remember, YZ plane on this figure is which plane? This plane, right? This is the YZ plane. So first what you are doing is first you are trying to find this green vector. So that is what we are attempting now. Now the vector n is elsewhere. I mean the vector n is elsewhere. The vector Tn will be elsewhere. Okay. But we now want to write this in these infinite possibilities perhaps can be reduced once you define this vector in terms of vectors which are parallel to the ijk plane meaning yz plane, xz plane and xy planes. So we are considering the yz plane right now. Okay, by making this cut. Now you consider the free body of the to the left of the plane mm. So this is essentially the free body which you should consider, and you divide the plane mm into a large number of small areas, each delta y by delta z. So each of these areas are of delta y by delta z dimensions. Okay, and so we will now repeat our arguments for the force vector and the force intensity for the arbitrarily defined plane with normal n by applying them to an element of area A in the plane mm. So we'll consider this small area and apply the same arguments which we have done before. Okay. Now on the small, which argument? This argument, this definition. Okay, you now have what delta A is. Okay, that is delta y into delta z, and you have a delta f force. You have the point obviously lying at the center of that area, and if you apply this to this particular figure, your traction vector will be the one which is actually this one. Okay, in the yz, perpendicular to the yz plane and parallel to the this axis, j axis. Okay. Okay. Let's see. Okay. So on this small area delta A, the small area delta A, which is centered on O, there will be a force acting delta F which is inclined to the surface mm at some arbitrary angle. So this delta F is just like in the previous case, aligned to an arbitrary angle to the normal of this area. Now you will describe the force vector delta F in terms of a set of rectangular force components, and the most convenient set of axes will prove to be a set in which one axis is normal to the surface and the other two are parallel to the surface. So let's see how that is done. Just like as I have said, this delta f is a this delta f of this figure is a vector. Okay, it can also be written just like any other vector, like this. Okay, so that will have x, y and z component, and that's what any vector would be. Now this is what this sentence in your textbook means. You want to describe this force vector delta f in terms of a set of rectangular force components. Okay, that part is clear. This is a Cartesian rectangular system in which you will have an x, y and z components, and the most convenient set of axes will prove to be a set in which one axis is normal to the surface and the other two are parallel to the surface. So one axis will be normal to this surface. Okay, sorry, let me show that over here. One surface, one axis will be normal to this surface over here. Okay, and the other two are parallel to this surface. So that is what we mean by this sentence. So right now we will take the small area delta x by delta y in this figure, okay, and divide this force vector into three components. One will be delta fx, uh, which is normal to the surface, and it also aligns with the direction of n, okay, because n is also coming outward of this area, small area, and the other two are parallel to the surface. So delta fy and delta fz are parallel to the surface. So you will have a delta fx, delta fy and delta fz over here, one normal and one parallel. Okay, now figure 4.5 shows these referred to along the axis. This we have already seen in figure 4.5. Now we proceed further with this. Okay, before proceeding further, it will be useful to adopt a convention for which allows us to identify precisely a specific area or space on the surface of the body. So for example, if we cut out a parallelepiped whose edges are parallel to the x, y and z axis, so these are the parallel, this is the parallelepiped, okay, and if you can see that the edges of this are parallel to the x, y and z. The edges are not the x, y and z axis, but the edges are parallel to the x, y and z axis. Okay, there's a difference which you can clearly see in this diagram. Okay, so there will be 6 separate plane surfaces which enclose the volume. You can easily see those 6 surfaces: 1, 2, 3, 4, 5 and 6. Okay, that's something which we already know for a parallelepiped. Okay, and we need to concise notation for unambiguously identifying each of these surfaces. So we want to sort of give a notation to this surface. Now we have already done that in chapter 3 and even in your mechanics course before, how to relate a face with a plane. So if a face will be defined as a positive when its outward directed normal vector points in the direction of the positive coordinate axis, and is negative when its outward normal vector points in the negative direction, coordinate direction. So by this definition, this particular face is a positive face because the outward normal of it is directed in the direction of positive coordinate axis, which is x. This face, okay, this face is negative because the outward normal to this is in a negative direction compared to this axis. That's why this is a negative face. Okay, something which we have seen before, but we are repeating it once again. So in this particular figure, face 1, 4, 5, 8 are positive. Okay, 1, 4, 5, 8 are positive faces, and 2, 3, 6, 7 is a positive Z face. I'm sorry. So 1, 4, 5, 6. So 1, 4, 5, 1, 4, 5, 8 is the positive Z face, and 2, 3, 6, 7, this is a negative Z face. Okay, so that's how we write this. Now with this knowledge, can you think of the face over here is a positive X face. Okay, because the outward normal of is along the same direction as the positive X axis. So hence its is a positive X face. Now if we return to this figure 4.5, okay, I'll just rub these parts over here. Now if you return to figure 4.5 and take the ratios delta fx, let's see. So we already know what these two things are. Delta AX is just this, okay, delta Y into delta Z, and delta F and delta X and every other thing is shown. So you want to take these ratios, delta Fy, delta AX, and delta Fz by delta AX. We have three quantities which establish the average intensity of force in the face delta AX. Okay, so these three quantities define to you the intensity of force on this face. In the limit as delta AX tends to 0, these ratios define the force intensity acting on the X face at the point O. Okay, so as delta AX tends to 0, remember this delta AX in reality has to be greater than the grain size or the atomic size, whichever scale you are considering. But since you are putting this limit of delta AX tending to 0, you are idealizing the fact that there is no grain structure, there is no atomic structure, and only thing is that the solid is continuous. Okay, that's an idealization which you are taking for continuum solid. Okay, so you have these three ratios, and in the limit delta X tends to 0, these ratios define the force intensity acting on the X face at the point O, and these values of the three force intensities are defined as the stress components. They are called the stress components associated with X face at point O. Remember, the point and the orientation or the face, both of these two quantities are always needed. It is not like a general vector anymore, in which you just had the magnitude and direction. No, magnitude, direction, and the plane also plays a big role over there. Okay. So these are the components, stress components associated with the X phase at point O, and they are called the components of stress vector acting on the X phase at the point O. Again, I am not writing, but that's what is implicit in it. As they are components of the stress vector acting on an element of area A whose normal points in the positive X direction. Okay. We note that we must use these two directions to define a stress component. You can clearly see that you have used two directions to define a stress component. Can you see those two directions? Direction 1, direction 2. In this case they coincide, but you see direction 1, direction 2, direction 1 and direction 2. So you have used two directions to define a stress component. One direction to identify the phase on which the stress component acts, and the second direction to specify the force component from which the stress component is derived. So essentially what we have just discussed. Now the stress components parallel to the surface will be called the stress components parallel to the surface will be called shear stress, okay, by the symbol tau, and that can be shown by tau xy. And similarly you will have the normal component that will be denoted by the sigma over L. So this is called normal stress. Okay, so we'll discuss these two things in greater detail in the next class. Thank you.